Welcome to Chapter 4, Discrete Random Variables. As always, I recommend you read the chapter in our textbook. Alright, so the first section of this chapter, 4.1, Probability Density or Distribution Function PDF for a discrete random variable. So a discrete probability distribution function has two characteristics, and these are two important characteristics you need to know. Number one, each probability, so each individual probability, is between 0 and 1 inclusive. In other words, and we talked about this last chapter about the possible values of probabilities. They can be 0, they can be 1, or any number in between. That's what they're saying here. Number two, the sum of all the probabilities on your list must always equal 1. Okay? 1 representing 100% of all possible outcomes. So we'll see these two rules applied in the next couple examples here. Speaking of which, there you go. So a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. So I'm going to give you all this data in just a second. They're saying let X equal the number of times per week a newborn baby's crying wakes its mother after midnight. So for this example, we're going to use 0, 1, 2, 3, 4, and 5. Okay? So that's what we're going to fill in for X. Remember, X are the values of the random variable. Okay. Oh, and in this case, P of X, the probability of X, this is the probability that X takes on some X value. Okay, in other words, if you actually look at it, what's the probability that the baby wakes its mother 0 times, or 1 time, or 2 times, 3, 4, 5, however many times per week? That's what that means. Okay? Alright, and I'm going to give you the probabilities here, so this is not something you need to know how to calculate. These probabilities will be given to you in problems like this. So for 0, it's 2 out of 50 probability. For 1, it's 11 out of 50. For 2, it's 23 out of 50. And the next one is 9 out of 50. And 4 out of 50. And 1 out of 50. Okay, so again, these probabilities are being given to you. All right, so the question that I'm going to ask here, is this a discrete PDF? All right, remember, there we go. Remember, a PDF is a probability distribution function. So we can answer this question simply by checking, do these probabilities follow both of these rules? It has to follow both of the rules. Okay, if even one of the rules are broken, then the answer is no, it's not a discrete PDF. So we check it for each individual probability. So each one of these lines is the probability between, somewhere between 1 and 0, or equal to 1 or 0. Well, yeah, all of them are between 1 and 0. Okay, so number 1 works. Okay. Number 2, the sum of all the probabilities must equal 1. So in other words, we need to add all these guys up. And if you do that, you'll see you definitely get 50 out of 50, which equals 1. So there we go. Number 2 is also satisfied. So yes, it satisfies. Oops, it. Satisfies both rules. Okay, so this is a probability distribution function. Okay, here's another example. Let's say a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Let X equal the number of times a patient rings the nurse during a 12-hour shift. For this exercise, we're going to use 0, 1, 2, 3, 4, 5, and P of X equals the probability that X takes on some value X. Why is this a discrete probability distribution function? So again, we're going to check it and see, does it follow both of those rules? Okay, so first we look at the individual probabilities here. Is each one of them anywhere from 0 to 1? And the answer is yes. All of these are between 0 and 1. All right, so rule number one up there is satisfied. Rule number 2, the sum of all of these must equal 1. Right? So you can punch that in and calculate it, right? So let's see, 10, 20, 30, 40. Yeah, this adds up to 50 out of 50, which is 1. So rule number 2 is also satisfied. So the answer is yes. This is a probability distribution function. All right? And that's it. That's as hard as those types of problems are going to end up being. All right, so more stuff with these PDFs. Mean or expected value and standard deviation. So the expected value, think of that phrase, expected value. It's the value you would expect in some sort of experiment. All right, so let's see. The expected value is often referred to as the long-term average or mean. Okay, so expected value is also known as a mean. This means that over the long term of doing an experiment over and over, you would expect this particular average, something that we'll calculate in a little bit here. You toss a coin and record the result. What is the probability that the result is heads? If you flip a coin 2 times, does probability tell you that these flips will result in 1 heads and 1 tail? You might toss a fair coin 10 times and record 9 heads. So remember, probability does not describe short-term results. Remember, probability is never a guarantee. Right? It just gives you information about what can be expected in the long term. In doing many experiments, then probabilities are usually pretty accurate. To demonstrate this, Carl Pearson once tossed a fair coin 24,000 times. He recorded the results of each toss, and he got heads 12,012 times. So that's illustrating the law of large numbers, and that's something we've covered before. All right, so that's really close to 50%. When evaluating the long-term results of statistical experiments, we often want to know the average outcome. This long-term average is known as the mean or expected value, and we'll use expected value quite a bit in this chapter. Let's see. Of the experiment, it's denoted by the Greek letter mu. So you've seen this letter mu before. Remember, that's your population mean. Make sure you know those variables. Let's see. In other words, after conducting many trials of an experiment, you would expect this average value. To find the expected value or long-term average mu, simply multiply each value of the random variable by its probability and add the result and add the products. So this is sigma notation, right? Remember, this just means add everything up. Okay? So in other words, what this would look like, you'll take the first x value and multiply by the first probability, the probability that goes with the first x value. Plus, you'll take the second x value and multiply by its probability. Plus, and we'll keep doing this, right? So plus all the way till you get to the nth, whatever the last one is. So x of n times the probability for that last x value. And that's going to give you your mean or expected value. Okay, so expected value example right here. So a men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. Probability that they play 1 day is 0.5, and 2 days is 0.3. Find the long-term average or expected value mu of the number of days per week the men's soccer team plays soccer. So first thing we're going to do is create, you don't always have to do this, but it makes it easy to visualize. We're going to create this PDF. All right, so we just take the data they told us. So let's see, so if they play 0 days, the probability is 0.2. 1 day, the probability is 0.5. And 2 days, the probability is 0.3. Okay, and just a refresher, right? This is a PDF because each of these probabilities is between 0 and 1, and they add up to 1. Okay, so now we're going to use the equation up there. So the mean is, we take the first x value, which is 0, times its probability. I'm going to use parentheses, so times its probability of 0.2. And we know that that answer is going to be 0, but we write it anyway just for the purpose of showing work. Oops. So plus the next x value, which is 1, times its probability 0.5, plus the next x value, which is 2, times its probability 0.3. And we can punch that in the calculator. You don't need to do the one with the 0. We know that's going to be 0. So if we punch this in and add it all up, we get 1.1 days per week. You're probably thinking, well, how can you play 0.1 of a day? Remember, this is a long-term average, okay? All right. All right, so another problem like this. Here we go. So here's an example. You're playing a game of chance in which 4 cards are drawn from a standard deck of 52 cards. You guess the suit of each card before it's drawn. So in other words, that's the clubs, spades, hearts, and diamonds. The cards are replaced in the deck on each draw. So this is with replacement. You pay $1 to play. If you guess the right suit every time, so all 4 times, you get your money back and $256. In other words, in the end, you win $256 in your pocket. What is your expected profit of playing the game over the long term? Okay, so X is going to be the amount of money that you profit. So think of that word, that you profit. You have to pay $1 to play the game. So if you play the game and you lose, your profit is negative $1. You lost $1, right? So you always got to be careful with the context of these problems. All right, and the probability of, well, so we've got to figure this out. And then they said the prize for winning is $256 total dollars. But we've got to figure out these probabilities. So right here it says find the probability of guessing the right suit each time, which would be, there's 4 different suits, right? So on the first card picked, you have a 1 out of 4 chance of choosing the right suit, right? And then this is with replacement, so whatever the card is, they put it back in the deck and you draw again. So, and the second one being choosing the correct suit is also 1 out of 4. And choosing the third suit correctly is 1 out of 4. And choosing the 4th suit correctly is 1 out of 4. Okay, because again, there's 4 different suits, and we're putting the cards back every time, so the probabilities don't change. All right, so this is equal to 1 out of 256. Okay, so the probability of guessing the right suit each time for the 4. So in other words, the probability of winning this game is actually quite low, 1 out of 256. All right, so that's the probability of winning. Now we've got to calculate what's the probability of losing, right? So winning and losing, what's that term we use in probability when 2 things are opposite of each other? The complement, right? All right, so the complement says the probability of losing equals 1 minus the probability of winning. Well, we just calculated the probability of winning, so 1 minus 1 over 256, and that equals 255 out of 256. Okay, just a little algebra there. So the probability of losing your dollar is 255 out of 256. All right, so now let's find the expected profit of playing the game. It's just expected value or mean again. So we're going to take the first x value, which is -1, and multiply by its probability, plus the x value for winning is 256 times its probability of 1 over 256. So if you punch that in your calculator, you will see you'll get 0.0039. So remember, this is in dollars. All right. Or no, sorry, this is, yeah. So you stand to gain about 0.39 cents per game, right? Okay. And that makes sense because the probability of losing is pretty big here, right? So if you play the game a large number of times by this average, again, this is not a guarantee, but by this average, you should win in the end. You should take in more money than you spent. Okay? All right. All right, the next thing we're going to talk about, and this is a really big, important concept in statistics here, binomial distributions. All right, so here's a quick example. Suppose Joe randomly guesses at a true-false statistic question. Joe's experiment has only two outcomes. Success is guessing correctly, and a failure is guessing incorrectly. Suppose Joe always guesses correctly on any statistics true-false question with a probability P equal to 0.6. So in other words, 60% of the time he guesses correctly. Then the probability of failure, so those so success and failure are complements, opposite, right? So 1 minus 0.6 is 0.4 for the probability of failure, and we'll use the letter Q for that. This means that for every true-false statistics question Joe answers, his probability of success is 0.6 and probability of failure is 0.4, and they will remain the same every time. Okay? So this experiment is an example of what we call a binomial experiment. Binomial experiments have the following characteristics, and these are important. You need to know these for sure. Let's see. So there's a fixed number of trials. Think of trials as repetitions of an experiment. The letter N denotes number of trials. And we've seen the letter N before, remember? Sample size. Same thing here. Number of trials, sample size means the same thing. The second rule here is there's only two possible outcomes, and we have to classify them as success and failure. That's important, and that's why it's called binomial. Remember, the prefix bi means two. In this case, two possible outcomes, either a success or a failure for each trial. So P is the probability of success, and Q is the probability of a failure. And so since those are complementary events, P plus Q must always equal 1. The last requirement, the third requirement there, the N trials are independent and are repeated using identical conditions. Okay, so if you have all three of these conditions met, then you have a binomial experiment, and you'll be able to use the process that I'm going to show you in just a minute here. Okay, so just the variables here for the binomial distribution. So N is number of trials, P is the probability of success, and X is the number of successes. Okay, those three are important. You need to know those. Okay, so N is number of trials, P is probability of success, and X is the number of successes. All right. You'll see some of the problems will ask you to find the mean of a binomial distribution. This is easy. These are just some equations you need to know. So mu, the mean, is simply N times P using the variables we just talked about. And a standard deviation, sigma, equals the square root of N times P times 1 minus P. And remember, 1 minus P is the same as Q, so you could also write this as N times P times Q. Remember, P is the probability of success and Q is the probability of failure. Okay, either equation works. All right, so let's do some of these examples. Now, some of these can get a little bit tricky, so I definitely recommend watching this video more than once to understand the different aspects of these problems. All right, first example, a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%. So, of course, the probability it does not successfully perform the trick, in other words, probability of failure, is 65%. Out of 20 attempts, let's find the probability that the dolphin succeeds 12 times. So when you do a binomial problem, so go through the three requirements, right? Fixed number of trials, yeah, they just said 20. Only two possible outcomes, success and failure, and that's what they said here. He either successfully performs the trick or he does not. And the third requirement, the trials are independent and are repeated using identical conditions. And yeah, it really doesn't say that, but we can assume that when the dolphin does these tricks, it's the same conditions. All right, so n, again, number of trials, so 20 attempts. P is the probability of success, and we always do P in decimal form, always decimal form, okay? And X, what's the number of successes we want to calculate? Well, they want to know what's the probability he succeeds 12 times. Okay, so we're going to let our calculators do this work because it could get pretty tricky doing it by hand. So on your calculator, you're going to hit the second button, top left corner, different color button, then the VARS button right below the keypad. And you're going to scroll down until you find binom PDF. Okay? So again, you're going to scroll down until you find binom PDF. Okay? Now it's important because you'll see two options. There's PDF and CDF. For this problem, we're going to do PDF. So, and let me show you something first, then I'll tell you some more details. And we're going to enter X, comma, we're going to do N, comma, P, comma, X. Now, again, on your calculator, you're going to see two options here, binom PDF and binom CDF. So, binom PDF is when they ask for an exact number of successes. Okay? In this case, they're saying exactly 12 successes. That's what we want to find out. What's the probability of that? Okay? So when they ask for an exact amount of successes, you're going to use binom PDF. So that's very, very important. All right, so we're going to plug this into our calculator. So you can do that again. Second, VARS, find binom PDF, hit enter, and you're going to enter, so it'll look like this, binom PDF, you're going to enter 20, comma, 0.35, comma, 12, and then hit enter. All right, and on these types of problems, since these calculations are probabilities, we're normally going to answer in two decimals properly rounded. Okay. Now again, when you're doing the My Open Math homework program, make sure you read the problem carefully. It may ask for more or less decimals. Okay. For now, on these these notes, I'm going to ask for two decimals properly rounded. So this one should round to 0.97. In other words, the probability that the dolphin succeeds 12 times out of 20 attempts in this example is about 97% of the time. Okay? So there we go. 97% probability. Okay, so that's the easy one when they ask for an exact amount of successes. But, of course, that's not always going to be the issue. So here's another example. It's been stated that about 41% of adult workers have a high school diploma but do not pursue any further education. Right? So if 20 workers are randomly selected, find the probability that at most 12 of them have a high school diploma but do not pursue any further education. So we have to be careful here. Think of that phrase, at most. We've talked about this before. If I'm going to give you at most $12, that means 12 or less, right? That's an important thing to remember. So at most 12 means 12 or less, okay? So, N, number of trials, right? So 20. Probability of success, this says 41%. And at most 12. Okay, so we're going to select 12 for X here. Now, on your calculator, you're going to do the same thing. Second, VARS, arrow down to binom, but in this case, binom CDF. Okay, so we use binom CDF when we have a greater than or less than statement. Okay, we use binom CDF on the calculator whenever it's a less than or greater than statement. So at most 12 means 12 or less. Okay, so we're going to use binom CDF still n comma p comma x. There we go. All right, so here we go. Find this on your calculator. So it's binom CDF, because it's an interval. It's a less than statement. We use the numbers we got, 20.41 and 12. And we punch that into our calculator. And what you should get is 0.97. So 97% of the time. I was looking at my notes wrong. So go back up to the problem right above here. You should have got 0.01. My mistake. That's okay. All right. So make sure you make that change in your notes. All right. So there we go. This one was supposed to be 0.97. All right. So whenever you have a less than statement, you're going to use binom CDF, right? So at most is a less than statement. Let's look at the next example, though, because we've covered exact amounts. That's a binom PDF. A less than statement is binom CDF. What about a greater than statement? Well, let's check it out. Here's an example. A fair coin is flipped 15 times. Each flip is independent. What's the probability of getting more than 10 heads? So now this is a greater than problem, right? All right, so let's find n and p first, and then we'll talk about x. So 15 times you're flipping the coin. Heads, we know the probability on a fair coin anyway is 0.5. But we have to figure out x here. So x is a little more complicated when it's a greater than statement. Okay, so here we go. We're going to look at this on a number line. So more than 10. So here's 10. Right, so more than means 11, 12, etc. More than. So what we're really saying is we want to find the probability that we get 11 or more heads. More than 10 means not equal to 10, which means 11 or more, which means we don't want 10 or 9 or anything below that. So in math, what do we do when we don't want values? We subtract, right? Subtracting is getting rid of the stuff we don't want. So this is what you've got to do. A less than statement is binom CDF. A greater than statement is the opposite of a less than. So we're going to use the complement rule. In other words, on your calculator, you're going to type 1 minus, then use the process second vars and find binom CDF, because this is an interval. Okay. And what we're deciding here is getting probability of getting more than 10 heads means we want to eliminate 10 and below. So our x is going to be 10 here. Okay, because we're subtracting binom CDF 15, 0.5, 10. We're getting rid of the calculations for 10 and below, which means our final answer will keep 11 and above, and that's what they want, more than 10. Okay, so punch that into your calculator. Like I said, you're going to do 1 minus second vars, binom CDF, enter those three values in. All right, and once you do that, you hit enter, and you should get 0.06. So in other words, there's about a 6% probability that if you flip a fair coin 15 times, you should get more than 10 heads. In other words, 11 or more. Okay? All right, so you can see the first one was pretty easy, right? The exact amount is just binom PDF. Less than statements aren't so bad. It's just binom CDF. But it gets a little complicated with the greater than statement. Okay? All right, so let's try a few more here just for practice. Let's see. About 32% of students participate in a community volunteer program outside the school. 30 students selected at random. What's the probability that at most 14 of them participate in a community volunteer program outside of school. So at most, again, if I'm going to give you at most $14, that's a maximum, which means we want 14 or less. Okay? All right, so first let's find our N, P, and X. So N, we're selecting 30 students. Probability of success is 0.32. At most 14 means 14 or less. So and that's what we're going to do with a binom CDF. X equals 14. So binom CDF 30, 0.32, 14. Punch that in. I should get 0.97. Okay, sorry, it should round to 0.97. Right, and that's as easy as these problems are. If you were doing this on a paper exam, which you're not in this particular semester anyway, but if future semesters of mine are listening to these lectures, this is the kind of work I would expect to see for full credit. Show me the calculator operation, show me the three numbers you're plugging in, show me the final answer. Okay? Alright, one more example and you'll be done here you'll be done with the lecture. You've got homework and studying to do, of course. So let's see, in the 2013 Jerry's Artorama Art Supplies Catalog, there's 560 pages. 8 of the pages feature signature artists. So suppose we randomly sample 100 pages out of the 560. And they're saying let X be the number of pages that feature the signature artists. So they want us to find some probabilities here. Okay? All right, and so if you look at the requirements of a binomial distribution, this problem satisfies that. So we're doing binomial again. So here we go. Let's find N. So we're sampling 100 pages. What's the probability of a success? In other words, a success here is getting a signature artist. Well, it says there's 8 out of the 560 pages that have the signature artist. And then X is what we're going to have to find for each of these 3 individual problems. Okay, so let's do this here. The probability, so let's find the probability that 2 pages feature these signature artists. This is exactly 2 pages, right? So we're going to say X equals 2. The N and the P will remain the same for all 3 of these problems. All right, so binom PDF, right? An exact amount 2. And we do NPX, so 100, 8 divided by 560. And you can type it in just like that in your calculator. It will make that calculation for you. And an X value of 2. And if you punch that in, you should get rounded to 0.25. So about 25% of the time, if you sample 100 pages out of this book, you should get exactly 2 signature artists. Okay? All right, number 2 here. The probability that at most 6 pages features the signature artist. So remember, at most is a less than statement. So less than 6. 6 or less. My apologies. So our X value is 6. So we do binom. This is an interval. It's a less than statement. So we do C, DF. And again, N, P, X of 6. Punch that into your calculator. You should get 0.999 something. I know this rounds to 1, but it's not really equal to 1. So you could put 0.99 or 0.999, I don't care. But just don't put a 1 unless the calculator tells you the answer is 1. Okay? All right, so there we go. So about a 99.9% chance that you get at most 6 pages when you sample 100. All right, number 3, the probability that at least 3 pages features the signature artist. So at least 3 means 3 or more, right? So think of that number line we did before. So here's 3, 4, 5, whatever, 2. At least 3 means 3 or 4 or 5. In other words, 3 and above, which means we want to get rid of 2 and below. Again, in math, when we want to get rid of something, we subtract, right? So we're going to do this again. So this is a greater than statement. So we're going to do 1 minus binom CDF, because it's an interval. Now look what we crossed out. We crossed out 2 and below, so this means x equals 2. Okay, so we got 100, 8 over 560, and x value of 2. Punch that in your calculator, you should get 0.17. Okay? Alright, so you can see with these binomial problems, there's quite a bit of work to do, a lot of thinking to do, a lot of understanding what's going on. Okay, so work hard on these problems, understand them,